So, a very warm welcome to BTH, to this Licentiate seminar for Martin. My name is Christian Johansson Askling. I'm the assistant supervisor for Martin. I've been that for a while now. And we also have at the top Tobias taking pictures, who is the main supervisor and also the examiner for Martin and for his work. So he's the guy with the decision today. In addition to us and Martin, we also have Åsa Eriksson from Luleå, University of Technology, who will be the opponent or discussion leader, whatever we call it opponent. So she will lead a discussion with Martin, but before that, he will present for 25 minutes, then Åsa will do about an hour-ish of a discussion together with Martin, and then after that, we will open up the floor for additional questions from anyone. So yeah, I think that's pretty much what I should be saying now, and then we'll let Martin run this part. Okay.
Thank you, Christian, and also from my side, welcome, and also to the guys online, welcome, and thanks for joining in. And yeah, so today I would like to present a little bit about the work I've done and my licentiate I wrote with the thesis, A Step Towards the Design of Collaborative Autonomous Machine, a study on construction and mining equipment. And so as Christian already mentioned, so we have 25 minutes, or I have 25 minutes. And here, this is just a kind of brief overview what we are going to touch upon during the next minutes. So first of all, I would like to give you a little bit of a background, since we are a kind of very diverse group here and not everybody knows what construction is, what mining is. So therefore, I try to bring everybody on the same page so that we more or less start from the same knowledge to jump then directly into the motivation and then for sure into the research question. After that, I would like to present my results, or at least some of them, and conclude with some words, and then last but not least, for sure, giving you a little bit of overview what I would like to do in the future with future work and how this research will be continued. But first, let's get started with some reflections on the background. So when we're talking about construction, then we may ask online dictionary or whatever to give us a definition. And I did that just to come up with that construction is the work of building or making something, especially buildings or bridges or roads, or we can name it infrastructure. But for us in the industry, in the construction equipment industry, already construction starts very early, where we started to extract material that it's utilized in the construction process out of the earth. And that is like this here, a kind of open pit quarry for basalt, or it can be sand, it can be gravel. All the materials that are needed throughout other construction processes are also classified as construction, how we internally within Volvo define that. And then once we have the material somehow extracted, construction also includes this. Everyone, I guess, knows this picture. It's a typical view you have when you're driving on the highway sometimes. Then it's road construction, where they either create new roads or renew existing roads. And these are typically done by big machines with a lot of people around this. But construction can also be like that, where we have static construction, creating buildings, the one we are in right now, universities, schools, hospitals, but also just simple houses to live in. In contrast to that, we can also ask, what is mining? And mining has also kind of interesting definition, or many interesting definitions, and I picked this one here. Mining is the process of extracting useful minerals from the surface of the earth, including the sea. And here, what's really interesting is surface does not mean that we pick it up. It means also that we dig a little bit into the surface, and that goes maybe goes on until 1,000, 1,500 meters down the earth. And this has then some different appearances. That can be big open pit mines, like the one here. It's an open pit mine in Nevada for mining gold. And as you can imagine, the type of machinery utilized here is much bigger than the ones I showed you before. So with the people here in this picture and the machine behind, you can just imagine that by the sheer size of the machine, what power and what energy goes in. But as I mentioned, mining also goes down the earth and in the earth. And so we have also kind of big machines in the earth extracting iron ore that we need to drive our society and to create all more or less the structures we sit on here. We have the windows, they are framed in steel. So therefore we need iron ore to get extracted mostly out of underground mines. And then I just combined these two in one slide just to show that, okay, mining and construction are activities changing the shape and appearance of the environment. So you can say for construction, it's just simple because there was nothing before, and afterwards, after the process is done, something is there at that spot. And the other, on the other side, for mining, there was a bank material, but if we are done with mining, nothing is. So you can more or less describe both processes in kind of mathematical form with subtraction and addition in a very simple way. And that leads me then to the conclusion that construction and mining activities can be described as highly dynamic in an ever-changing environment. And this is very crucial, especially when we talk later about the term autonomous. But we are not just doing construction and mining because it's fun. We are doing that because we would like to, for sure, create some benefit. And then usually some economic guys coming in and they measure stuff. And here what they measure is productivity usually. And here I just depicted two kind of famous slides that are very often used to just show that the construction and also the mining areas are lagging behind in terms of productivity, especially when compared with, in that case, manufacturing. Here in construction, you see that there is a big difference, and on the right side, it's also manufacturing, very productive in that sense, and mining is just very, very, not unproductive, but it is not as productive as mining. But here, what is not mentioned in these slides, but what is mentioned in the reports, is that the productivity here, it's based on a term called labor productivity. And this is defined by the quantity index of gross output per quantity index of labor input. That means every hour that someone works here is also defined here, is going into the productivity. And so it is, on one hand side, good to utilize this for comparisons, but it's bad if you have a labor-intense industry, and therefore it's maybe not the best way of defining productivity. When we internally define productivity, for sure, then we very often talk about machines, and then there the productivity is defined as mass per time unit, and then we can also derive efficiency, and this is mass per used energy. But then, just keeping this in mind, we know that if we reduce the number down here, we can maybe increase the productivity, and this is what a lot of people think would be kind of nice. And so they would like to drive autonomy as a kind of key driver to increase productivity for the whole industry sector. But I challenge that a little bit. But I would say that automation and digitalization can improve competitiveness in the industry, because here we have some possibilities to increase actively the production process on the side. We can then also improve the safety, because we have all the sensors available, all the systems then to know what's going on at the specific operation, and then mitigate dangerous situations and so on. We can overcome labor shortage, what's more or less a big issue here in the Western developed countries, where we see that, okay, we are running out of very skilled workers, and maybe automation can support here to fill this gap. And we, on the other side, have a possibility to develop skills in the undeveloped countries, where we then can utilize automation and digitalization to bring unskilled workers or unskilled operators to a higher level in a much faster time, so they don't need to learn 10 years how to efficiently operate a reloader or excavator or a hauler, so they more or less can shrink down this amount of time to a very, very short period. And then we can also, by utilizing automation and digitalization, contribute to the sustainability goals stated by the United Nations. But let's talk a little bit about automation. And a lot of you guys have maybe heard about the autonomous driving, autonomous car, and usually then it's defined as automation level. And I just redraw this picture here from the SAE, where we have 6 distinct levels of automation, from reaching from no automation to full automation. And in between, we have different steps where we subsequently adding more, in that case, driver assistant functions to ultimately come to a full automation solution on the very right side here. The study I'm focusing on here right now in this small textbook is more on the right side here with high automation and full automation. But the skill development, as I mentioned before, is more happening here with operator assistance, partial automation, and conditional automation. So there we can actually make a huge benefit for training and people developing them to a higher level of skills. But what motivates me when it comes to do the research? And I just found this quote from Claudia Eckert that's more or less summarizing my intention quite well. So designers hardly ever start from scratch, but design by modifying existing products. Complex products such as aircrafts, jet engines, or maybe construction and mining equipment evolve from generation to generation, often over decades, through the transfer and revision of design elements. So when it is about defining and designing traditional products, that is, I would say, the way of doing it. But when we're talking about a fully autonomous solution, maybe that's not the right way, because if we just automate what is existing, then we're leaving a lot of potential on the way, and we're not getting as much out of the design task as we could be. By that, I defined some research questions, and one of them is, how can requirements for the development of autonomous machines be discovered and captured? Followed by a second one, how can different interactions of autonomous mobile machines be described? Because we know that interactions will happen. If we see what's happening today on the construction and on the mining side, then we also can estimate that this will also happen on a fully autonomous side. So therefore, it needs somehow to be described in a good way. So let's start a little bit with autonomous system design. So autonomous system design involves, for sure, the machine design. So we should come up with a design for an autonomous machine that is working or carrying out a task that it should do. So the job to be done, so to say. But we also need to think about infrastructure design. Do we start from a fresh field, and are we doing a kind of groundbreaking activity, or do we have an existing infrastructure that needs to be adapted to the new autonomous situation? So this needs also to be involved into the overall design of the autonomous system. And then we also need to think about service design. So is it the way that we create a machine and then we hand it over to the customer, like a vacuum cleaner, and say, okay, it will find its way, and you know how to operate your operations, and then it's enough? Or is it something that we have a partner relationship with our customers to really define, okay, this is what we are going to do, and this is how we can, over the offering of the machine, contribute to your benefit and to your operational result in the end. Internally, we have run a research project together with Skanska and other research partners, where we try to somehow more or less do all of that at once. And it was the electric site project, where the goal was to reduce, for sure, the carbon, the CO2 emissions, but it involved also all these aspects here. So we had these autonomous, fully electric load carriers. We then adapted the infrastructure, because these load carriers are fully electric, and usually it's not the case in a quarry industry. So therefore, all these charging infrastructure need to be included. And then we also needed to think about, okay, when we're dealing with electricity instead of fuel, so what kind of services emerge from this new way of maybe trading the energy? So therefore, that was a kind of interesting approach, and that is not just a nice rendering. It's really real stuff, I would say, and it was active for some weeks last year, and it's going to be in the first customer pilot next year, early next year. So this is really happening, but as you can imagine, as a researcher, you don't have too many possibilities to just go there and do some research and test some hypotheses. So what we have done then instead, we utilized the scale site that was here for some years, weeks at the BTH, and also the colleagues here took care of this site during the last years. And we utilized this site as a kind of demonstrator, but also to prototype different solutions. So we utilized experience prototyping to generate data. So this is more or less than a real data mine, you can describe that. We used and tested interactions we tested interaction hypotheses and collected feedback through observations, surveys, and interviews. And we prototyped new services and solutions in a scale scenario. So we have not been utilized too much money or too big investments to test stuff. We could just utilize this scale site that was already existing to make some decisions if a concept has a value or if we should go back to the office and rethink much more. What we also figured out that facilitation of collaboration and interaction is key, and therefore we also started to think a little bit about that. So just as a small thought experiment, imagine this machine has no driver on it and is coming up to you with full speed, and I guess everyone would like to know if the machine has recognized me. So am I safe in my position right now? Should I change my behavior? And so that is something where we thought, okay, communication would be nice to have, especially if we're dealing with autonomous machines and humans sharing the same work area. So sharing machine intentions would be really nice, and that can be done by different ways of communication. Then sharing also this information can facilitate the collaboration, and this is for sure also one main aspect of the communication, especially the on-site communication. We know that facilitating the trust development is a big part of communication, because if you trust and if you can have a long-term perception of what the machine is doing, then for sure there will be a natural trust development between the human and the autonomous machine, and therefore also then the productivity level will be much higher than if the human constantly mistrusts the system. And for sure, safety is also a key part when it comes to on-site communication. So we can increase that really, really much. So that was just a proposal we got from a student collaboration with Stanford and BTH here. So that is just how it could be. It's not a final product, but it was a nice prototype to just test. Okay, we have different artifacts that can be utilized to show machine intentions, to show it to the user and to the human, and also to get some more information distributed if that is needed. But the overall idea was to keep the human productive and not to have him slowing down his operation, or the machine should not slow down its operation, and so we can keep a high level of productivity. Based on that, I started to develop an initial interaction model, and I placed the autonomous machine or the autonomous system in the middle. Around that, there are different other building blocks, and they are just here in this matrix style. And so what we need to do is, for sure, we need to connect them. And the quite obvious connection is the connection of load and material transfer. If because that is the main purpose of machines we are going to produce. So they should transfer load from, the machine should transfer load into the site infrastructure. That could be a crusher, could be a hopper, could be a sorting machine, or screening machine. And also machines among each other should transfer load. And here we have then also autonomous machine transferring load with a non-autonomous, I would say, old-style mobile equipment machine. In the next step, we're adding more communication or more interfaces, and this is the information. So just numerical information about load, about heading, about speed, and this is then for sure coming from the control system to the autonomous machine. The autonomous machine among each other can exchange these type of data, but then down here we have a dashed connection, and that means maybe we have the possibility that this old type of equipment is exchanging data, or we don't have the possibility. So it's all about transmitting and receiving data. But we need to include that into this model already, because there can be possibilities out there in the field that we find older equipment that has not the possibility to receive any numerical data from an autonomous system. And next information exchange is the qualitative information exchange. So here, that is kind of information that needs to be interpreted by the machine, especially when we have to deal with humans. Here, the machine needs to understand to some extent what the human tries to tell the machine. If it is voice, if it is gesture, if it is some pointing. So that is a model-based approach then, that the machine needs to be able to just recognize, okay, this is going on. But the other way around, also then humans need to recognize what the machine is going to show them, or what the machine wants to show them with specific actions or specific communication tools the machine has on it. Then the next level is the physical interaction. And here we have some interactions we would like to facilitate for sure. This is when we have a manual control of the machine by the human operator or the human collaborator. This is then also kind of intended physical interaction, also with the environment. We should support the machine, so we would like to have interaction with the ground, with the material we are going to break or to load. But we also have unintended interactions. And this is quite a tricky part, because on the one hand side, we allow interactions with the environment, and on the other side, we would like to suppress interactions with the environment, so we don't want the machine to run over any objects, especially if we have humans in the site. So here it's kind of tricky, but it is going into the interaction model and should be somehow captured by the model. And then we have here this very lonely block in the lower right corner. And this is something, so the known unknowns. We know that there is much more stuff we need to consider, but right now we don't know exactly what it is. So therefore, I added this block here just to capture there is more stuff we need to consider. And since there is more stuff, we also need to add all possible interfaces. And by that, we're having a kind of initial interaction model that can be utilized to bring the research a little bit further, and then to more or less describe the autonomous machine when it comes to interacting with humans and the site and infrastructure. So in the next step, I would like to go a little bit on the to show you what I did as in the performed research, just briefly describe in paper 1 what was the key finding. So a key factor for in that paper was that the different connectivity throughout the different layers on the machine level, but also to the control level, is key for enabling automation. The second paper more or less deals with a prototyping system that can be used as, for sure, prototyping communication tool, but also to generate more useful data that is then afterwards utilized in the product development. And the third paper focuses on the trust as a basic collaboration principle between humans or human co-workers, and then also between humans and the autonomous machine. As a conclusion, just revisiting the research question, I can say that utilizing observations and interviews of current site staff can be really beneficial if we try to create a new autonomous future, because we don't have the possibility to go to autonomous sites. They don't exist, but we can carefully choose and utilize all existing information right now to forecast what will happen when we add autonomous features. Then data mining and need finding with respect to autonomous machines can also be very helpful to discover and capture requirements that are then subsequently utilized in the product development process. And an interaction model can also be very useful when you start to develop very new features into machines, so that you don't forget to have very, very crucial parts in your design. And then the second question was, how can different interactions of autonomous mobile machines be described? And here, that was just the last part. Employing an interaction model can be crucial for the interaction styles. And then we have physical and cognitive interactions. And then finally, we have then also intended and unintended interactions that needs to be captured. In the future, I would like to go a little bit more into the refining of the interaction model, expand the model and map the full site interactions for sure, and ultimately that will then lead to a creation of digital twin for site representation that is then also part of the next research steps that will come. Saying that, I would like to thank Volvo to enable this research. I would like to thank BTH also to host me as a PhD candidate. I would like to thank Jenny for pushing me through, and also Ulrich, Christian, Bobby. I would like to thank Christian and Tobias for supervising me, and my family partly here also for their super support, and for sure Ryan, always there for discussion. Thank you all, and by that I'm opening for questions. And
okay.